Hi guys, and welcome to another production of materials video. Today we're going to be looking at batteries and specifically the calculations involved in using two half cells to create an electrode potential. So here's a battery. Well, it's something that we call a battery. The purpose of a battery is to convert chemical potential energy into electrical energy. That's what we get. We're using the stored energy in the chemicals in order to produce electricity. The energy that's produced can be represented by a voltage or an electromotive force, or EMF. And we can calculate these values for different combinations of cells. We describe the electromotive force, or the voltage, across the electrodes when a very small current is being drawn. So that will represent the maximum voltage that the cell can deliver. The EMF is usually dependent on the types of electrodes that are used, and also, generally speaking, whether or not those electrodes are participating in the reaction or are simply part of the devices that we use to ensure that the circuit is closed and the current will run through the entire circuit. Now, one of the things that we do with our table of standard reduction potentials is that we use a standard for comparison. We've done this in the past, and the standard for comparison in as far as galvanic cells are concerned is the hydrogen electrode. And that's why when you look at the table of standard reduction potentials, the value for hydrogen is 0.00 volts. So effectively, everything else is being compared to the hydrogen half cell. So we need to know what conditions we need in order for our galvanic cells to operate. So in order for us to make sure that we have reliable and accurate results, there are a couple of important conditions. Firstly, we need a 1 molar solution of the electrolyte. So this solution here is going to be the electrolyte. It's going to allow the passage of ions. And so we need to make sure that that solution is at 1 molar concentration. We need to make sure that the temperature and pressure are standard laboratory conditions, 25 degrees and 100 kilopascals. If we don't have this, then there's a possibility that we may result in an EMF or a voltage that does not correspond to the theoretical value. It's not important for you to be able to remember all of these because you're going to be provided with a table of standard reduction potentials. So this table is the one that you will see that we take out of the data sheet that accompanies your exams. And you'll notice that they're all written as reductions. So they're often referred to as the standard reduction potentials because you can see they all involve gaining electrons. And as a consequence of that, they're all reduction. In order to calculate the overall EMF of the cell, then what we need to do is this is an electrochemical cell. For the ones that we're looking at, electrolytic cells are the ones that use electricity to break down chemicals. So in that case, we're going from electrical energy to chemical energy, which would be exactly the same calculation, just in the reverse direction. So make sure when you're doing these calculations, you remember that we need 1 reduction and we need 1 oxidation, and therefore one of these reactions is going to have to be written in the reverse. And when we reverse it, we also must reverse the sign as well. So here you see a slightly bigger version, one that maybe you can actually read a little bit better. And you'll notice that here is the standard, the 0 value. So we have arbitrarily set hydrogen as the standard, and so therefore everything else is compared to hydrogen. Now we could just as easily have said anything else. For example, if we decided we were going to set copper as our standard, then it would just mean that everything in the table just gets moved. In this case, by a number corresponding to 0.34 volts. But the table is just a comparative table, and it only becomes useful when we've got 2 half cells together, one oxidation and one reduction, and then we can look at calculating our overall value. So how do we do that? You'll often see the symbol E0 that corresponds to the calculation of the EMF, or overall cell voltage. And in order for us to calculate it, we need to have one oxidation half reaction and one reduction half reaction. When we put these together, one of which will have had its equation reversed and its sign reversed as well, then we can just add up the values in order for us to get the overall standard electrode potential. So the E0 value for reduction plus the E0 value for oxidation gives us the E0 value for the overall cell. All the standard electrode potentials that you look at are reductions, and that means that one of them at least is going to have to be reversed in order for us to get a redox couple, an oxidation and reduction. In more specific terms, what we're actually looking at is the amount of energy involved in gaining the electron. So because reduction is gain, we're actually looking at an equivalence value for what energy is required or is involved in the gaining of electron by a particular atom or polyatomic group. When we look at the oxidation, as I mentioned before, you just reverse the sign of the E0 value and then you'll have the two together, so we have an oxidation and reduction couple. So here's two, the way they're written. So this is gaining of electrons, so this is reduction. So oxidation is the opposite direction, and when we reverse the reaction, we also reverse the sign. Same thing for sodium. The first one is written as the reduction, and the second one is the oxidation, and because again we've reversed the direction, we must reverse the sign. So a positive becomes a negative, and a negative becomes a positive. So if we're going to try and find values, then what we need to do is we need to look at the EMF of the individual ones in order to determine what's going on here. So here we have a zinc anode, so we know that oxidation occurs at the anode, so that means that the zinc is going to undergo oxidation. The zinc here is the equation. For zinc, we have a zinc solid going to zinc 2+ ions and releasing 2 electrons. Those electrons are going to move from the anode to the cathode. And the second half equation will involve copper gaining those 2 electrons and becoming copper solid. Oxidation at the anode and reduction at the cathode. So we need to look at each of these two equations. Here's the overall equation. The zinc solid is becoming zinc ions and the copper ions are becoming copper solid. So we put each of these two together into two half reactions, and then we use the values that are in the table in order for us to calculate the value. Notice that we've had to reverse the sign for this one. So the value for the standard reduction potential for zinc is minus 0.76, and therefore when we reverse the direction to make it an oxidation, we have to also reverse the sign. So the copper will be written as the reduction, so this is the ox and this is the red, and as a result of that, when we add them together, we get this reaction up here, and we get this particular cell voltage, which is 0.76 plus 0.34 to give us 1.1 volts. Now, if the E0 value is a positive value, then the reaction is a spontaneous reaction. And as I've mentioned to you before, this is a good way of determining not only whether or not a reaction will occur, but how vigorously that reaction will occur. If the value is a negative, then it's not a spontaneous reaction. If we were to put one substance with the other, then we would see no reaction. The only way we can get a reaction to occur in this case is if we actually put electrical energy into the system of a value equivalent to what we calculated as the magnitude of the negative voltage, and that will then cause the reaction to occur. That would be an example of electrolysis, where we're actually putting electricity in order to get some sort of a reaction to occur. An electrochemical cell is one where the electricity is generated from the chemicals within and must have a positive value. Why don't we double the value? This is one thing that's come up previously. Okay, the reason we don't is because the E0 value is a ratio of energy to electrons. So the amount of energy per electron. It doesn't matter how many electrons there are, we still get that amount per electron. So that's the way that this works. So when we double the values, or we triple them, or we change the sign in order to ensure that the number of electrons for both the oxidation and reduction half cells are equivalent, so they can cancel when we add them together, we don't change the value of the E0s. They are always going to remain the same. The only thing that may change is their sign. Okay, so magnitude will not change, but sign may change. Change when we reverse the reaction. So here's a question from quite a few years ago now, but you can see I've mentioned to you that this syllabus has been examined for a long time, so there's plenty of questions for you there. So in 2001, question 18 was actually a 6-mark question. It had 3 parts to it altogether, but because of space, I've just thrown the first 2 parts in. So galvanic cell made by connecting 2 half cells. 1 half cell was made by putting a copper electrode in a copper nitrate solution, so that's this one over here. And the other half cell was made by putting a silver electrode in a silver nitrate solution. The electrodes were connected to a voltmeter as shown in the diagram. And the first part of this was to actually draw in the salt bridge. Hopefully you've realized that this is actually not a complete circuit yet, and we're going to have to add a salt bridge in and make sure your salt bridge actually goes under the level of the electrolyte in each of those cells. It needs to make sure that it's in good contact. We label this as a salt bridge, and it's probably also worth identifying that something like potassium nitrate solution is what is actually in the salt bridge. So we add that first of all, and after that what we need to do is we need to calculate the theoretical voltage for this cell. Now I'm not going to do that, but I'm going to get you to ask me the answer to that question, and I'll answer it for you when I next see you. Thanks for watching.